ever since the telescope came onto the scene in the 17th century, we've wanted bigger and better ones that would let us peer ever deeper into the cosmos. Sure, size isn't everything when it comes to an observatory, but a giant mountaintop observatory generally tells us a bit more than a handheld spyglass. And ever since we've been making telescopes, we've also been making them better. So here's a quick tour through some of the biggest telescopes, past, present, and future. Let's start with an early biggest telescope. The so-called Leviathan of Parsonstown wasn't given that nickname for being small, after all. These 19th century astronomers went to a lot of trouble to make their huge telescope operational, but it was worth it. Here's Hank to tell us how.
About 200 years ago, astronomers had a bit of a debate on their hands. In the late 1700s, astronomer Charles Messier had put together a list of more than 100 objects that appeared fuzzy or nebulous in his telescope. At the time, it was the world's best catalog of these so-called nebulas. And as Messier's discoveries piled up, astronomers fiercely debated a simple question: what were they? Some thought these objects were hundreds or thousands of stars too small to be clearly resolved. Others thought their strange glow came from a gas-like substance floating in space. The only way to figure it out was to build a bigger telescope. And that is where the Leviathan of Parsonstown came in. A telescope larger than any in the world, built into what became basically a small fortress. The Leviathan was constructed on the grounds of Birr Castle in Ireland, home to William Parsons. A mathematician by training, Parsons returned to his estate in the 1830s after a successful career in politics, and there he used his new free time to build and study several telescopes. But his legacy really began in 1841 when he took over as the Earl of Ross from his father. The new title gave him the resources to put some of his engineering ideas to the test with a telescope of unprecedented size, one big enough to finally identify Messier's nebulas. Except, no matter how many fancy titles you had, it was incredibly difficult. At the time, the world's largest telescope had a mere 48 inches in diameter, around 1.2 meters. Parsons wanted to build one with a diameter of 72 inches, or 1.8 meters, which would collect more than twice as much light. But adding those extra 60 centimeters was much easier said than done. Today, telescope mirrors are mostly made of glass, with a thin coating of a metal like aluminum to provide the reflective part. The glass creates the shape, and the aluminum adds the shine, resulting in a mirror that is relatively light and resistant to tarnishing. But in the 1800s, mirrors for telescopes were cast out of a bronze alloy called speculum. Speculum was about as reflective as materials got back then and was relatively easy to work with, but to make a mirror almost 2 meters in diameter required 4 tons of metal to be melted and then slowly cooled over a period that would stretch from weeks up to 4 months. Also, to focus the light well, the rough mirror, called a blank, needed to be shaped into a virtually perfect parabolic curve. Traditionally, this was done by hand. But in the spirit of the Industrial Revolution, Parsons developed a steam-powered machine that rotated the blank underneath an iron polishing tool. Still, polishing the blank required 2 months of painstaking work, and it took him and his laborers 5 tries to successfully cast and polish such a massive mirror. And then they had to make another one. See, speculum was highly reflective, but it also tarnished really quickly, so keeping the telescope in operation required alternating between 2 mirrors. And that was only one part of the design. At the same time, his team was also constructing a wooden tube for the mirror to be mounted in, which extended nearly 18 meters. The tube was attached to the ground at one end and could be pointed up and down using a pulley system that weighed 150 tons, so much that everything was supported by 2 massive stone walls. And you are starting to realize now why they called it the Leviathan. That stone fortress did the job, but it also left the telescope with one huge flaw. While it could be pointed up or down at basically any angle, the walls prevented it from turning left or right. So looking at a specific spot in the sky meant waiting until the Earth had rotated just right for the object to come into view. And then, of course, they would stop the Earth from moving so they could look at it. No, the Earth is always moving, so keeping an object in view required a team of 5 people to manipulate the pulleys. Being the observer also was no picnic. Photography technology was in its infancy, so observations with the Leviathan were made by standing in a small cage at the top end of the tube and peering through an eyepiece. Then, you had to just sketch whatever you saw on a nearby easel. Now, this all sounds a little bit primitive, but apparently Parsons and his team were decent artists because those sketches helped answer the question of nebulas and revolutionized astronomy. Within a month of the Leviathan's completion in 1845, Parsons shared a sketch of the object known as Messier 51. It showed a collection of individual stars arranged in a spiral structure. Parsons was convinced that these stars moved together as one cohesive object, and he was right. He didn't know it, but this was the first ever detailed observation of another galaxy, and it would not be his last. In time, Parsons, his son, and their assistants would identify 57 so-called spiral nebulas, of which 48 we know now are galaxies. And at the same time, he also definitively proved that other nebulas weren't made of stars, but of brightly glowing gas. So a thing that is extremely unusual in science happened. Two groups of people disagreed about what something was, and they were both right. These days, you can still visit the telescope, but its days of serious research are long gone. The Leviathan remained in use into the 1880s and was eclipsed in size in 1917 by the 2.5-meter Hooker telescope at Mount Wilson Observatory in Los Angeles. But it is still a landmark in science history. I hope to be able to go visit it one day. It helped to settle a major debate and started to reveal that the universe is far bigger and more interesting than just what's in our galaxy. It was also an incredible engineering achievement, from the artistry needed to make the mirrors to the stone walls that held it all together. So if you ever find yourself near Birr Castle, stop by and say hello to one of the greats, tucked away in Ireland.
These days, we have more than just optical telescopes. There are so many kinds, it's hard to definitively hand out the prize for the biggest one. For example, what if your observatory is really 66 mobile radio dishes in a trench coat? Why, then you have ALMA, a huge observatory that's helping us study some of the oldest and most interesting parts of the sky. Caitlin, tell us more.
The space telescopes orbiting Earth tend to get a lot of attention. It seems like there's always some beautiful new Hubble photo or a couple of new exoplanets discovered by Kepler. But there are some amazingly advanced ground-based telescopes too, and some of their coolest discoveries have come from ALMA, a telescope that's been observing the universe since 2011. ALMA, or the Atacama Large Millimeter Submillimeter Array, is made of a set of 66 telescope dishes stretched out over the Shenandoah Plateau, part of the Atacama Desert in Chile. The phrase millimeter submillimeter describes the chunk of the electromagnetic spectrum that ALMA detects, wavelengths that range from about 1 millimeter to about 10 millimeters on the shorter wavelength end of the microwave spectrum. Its huge array of dishes gives ALMA the highest sensitivity of any millimeter submillimeter telescope in the world, and since it's the best in its class, ALMA is always being used to observe and re-observe stuff in space. And some of the telescope's most amazing finds have taught us about everything from new exoplanets to ancient star formation to giant glowing clouds of hydrogen. Like when astronomers use ALMA to clear up the controversy around a star called Fomalhaut. In 2008, the Hubble Space Telescope discovered what looked like an exoplanet around Fomalhaut. It was the first discovery of its kind. All the exoplanets discovered before that had been found indirectly, through clues like changes in the star's light. But you could actually see this planet directly. It looked like a denser point of light in the enormous diffuse disk around the star. And even though astronomers were pretty sure they'd discovered a planet around Fomalhaut, they weren't totally sure. Because the visible material in the disk, which is mostly small dust particles, does two things. First, it scatters lots of visible light. So if you're observing it in the visible wavelength range, the dust is very bright. And second, the force from solar wind from Fomalhaut can be strong enough to move those dust particles around. So astronomers knew that the images of the disk taken in visible light didn't necessarily correspond to the actual underlying disk structure. So that planet Hubble found, it might not have been there at all. And that's where ALMA came in. In 2012, astronomers decided to study the disk around Fomalhaut in millimeter submillimeter wavelengths, which would allow them to see past the haze into the deeper structure where more massive particles live. When they used ALMA to observe the disk, they saw a very sharp and well-defined inner structure, which basically looked like a ring of larger particles. And based on computer models of the ring, they found that it's probably shaped by a couple of shepherd planets, which orbit on the inside and outside of the ring and sort of corral the particles. Which means that thanks to ALMA, we now have a lot more evidence that there really is a planet around Fomalhaut, maybe more than one planet. So ALMA can see deep into a star's disk, but it can also see deep into the ancient universe. As the universe expands and sources of light move away from us, the light we see essentially gets stretched out so it has a longer wavelength in what's called redshift. If visible light gets stretched enough, it isn't visible anymore because it's gone past red and into the infrared or even microwave range. This means that really old distant things are invisible to our eyes and to telescopes that can't detect long enough wavelengths. But we can detect those things if we tune into a lower energy part of the spectrum, like say the millimeter sub-millimeter range. So ALMA can see really ancient light. Astronomers have been using ALMA in an ongoing project to reobserve Hubble's famous ultra-deep field image. The ultra-deep field shows a ton of galaxies in a tiny section of the sky, the size of a grain of sand held at arm's length. I mean literally tons. There are about 10,000 galaxies in the image, but we know that there's even more in that section of the sky, so astronomers are using ALMA to see what Hubble couldn't. And last year they found that ancient galaxies in that section of the sky, like 10 billion years old kind of ancient, had high concentrations of carbon monoxide, which is associated with star formation. They already knew that around the same time there was a huge peak in star formation in the universe, but they weren't sure what caused all that star formation until they used ALMA to observe those early galaxies and found the abundance of carbon monoxide. And now we know that the gas must have provided the right conditions for the stellar baby boom. ALMA has also helped us learn why some of the largest objects in the universe are glowing, specifically these ridiculously ancient huge structures called Lyman alpha blobs. They're called that because they have a very well-defined Lyman alpha spectral line, a specific wavelength of ultraviolet light that's emitted by hot hydrogen gas. So we knew that there were these huge luminous clouds of hydrogen just floating around in space, but we had no idea why they were glowing until ALMA. Astronomers using ALMA found galaxy clusters inside the Lyman alpha blobs. And it turns out that these galaxies are forming stars at an incredibly high rate and emitting lots of Lyman alpha radiation because of all the hydrogen in those stars. The radiation then scatters off of the surrounding gas cloud and we see an enormous blob. So now, thanks to ALMA, we know why Lyman alpha blobs glow, because of all the galaxies making stars inside of them. So even though ALMA's only been around for a few years, it's already taught astronomers a ton about the universe. And with the constant flurry of papers being published with discoveries made using ALMA, we're always learning more.
ALMA's design, using multiple telescopes working together, helps us build a bigger observatory. Such collaborations have resulted in telescopes basically the same diameter as Earth, but it's possible that in the future, we may stretch the definition of telescope into something even bigger. No, bigger than that. Much bigger. Just roll the tape.
I would like for humans to take a picture of an exoplanet. I mean, we can image them, by which I mean you can see the little points of light that are planets in other solar systems. So that's kind of a picture, but I really want to see one. You know, like we're flying up to it in a sci-fi movie. I want to see the clouds and the continents, and that, of course, is impossible. Except it's not. We just need bigger, badder telescopes. And you'd be surprised how creative astronomers can get when it comes to coming up with them. A telescope is really just two things: some way of focusing light and some way of detecting light. This can be as simple as, say, a lens and Galileo's eyeball. These days, it's more along the lines of mirrors and tons of different cameras and detectors. In theory, though, to get better and better photographs of distant objects, you just need a bigger lens or a bigger mirror. Just a system to collect more light. Galileo's telescope had a 38mm lens. And from there, we've scaled up to the James Webb Space Telescope's 6.5 meters up in space, with even larger mirrors down here on the ground. Like currently under construction in Chile, the appropriately named Extremely Large Telescope will have a 39-meter mirror. But those are just peanuts compared to some telescopes we're already using. See, there's no reason the detector and the lens of a telescope have to be in one piece. In theory, you could have a telescope that is very, very, very long, with a detector literally light years away from the lens. And indeed, those telescopes exist thanks to gravity. Gravity warps space. Specifically, very massive objects distort space around them. And warping space causes light passing through it to bend as well. And Bending light is what the lens of a telescope does. And in very particular situations, this effect creates an accidental telescope. This is an Einstein ring, a weird ring around a massive object in the sky. The stuff you can see around the star is not actually there, it's behind the star, way behind it. The light coming from those extremely distant objects is being warped by the divot the star makes in space, allowing us to see stuff that is very, very far away as if it were much closer. Gravity is warping the space, so we call this gravitational lensing. These accidental telescopes are how we know a ton of stuff about our universe, including seeing some of the most far off and therefore earliest stuff out there. The James Webb Space Telescope will be able to use gravitational lensing, effectively pointing a telescope at another telescope to make some seriously superpowered images, potentially seeing some of the very first stars to ever exist in the universe. Many objects, such as stars, galaxies, and even black holes, can create a gravitational lensing effect, but almost none of them are useful because we can't control these telescopes. The detector, which is us, and the lens, which is the star, have to line up perfectly with the object we're observing, and all by pure astronomical chance. Luckily, even though space is very empty, it's also very big, which means there are lots of opportunities to get lucky. We've identified thousands of these alignments that have allowed us to discover all kinds of cool things. But we really don't have a choice about what's being lensed. Except here's the cool part. In the future, we might. That kind of control would let us use gravitational lensing to do all kinds of things, including taking an actual photograph of an exoplanet. Photographs could show us if they have continents, clouds, oceans, who knows? In 2021, an article called Image Recovery with the Solar Gravitational Lens was published in the journal Physical Review D. And by solar, they don't mean any old star out there. They mean our sun. This is just the latest proposal for a solar gravitational lens, an idea that goes back decades. What's different about this one is that it considers what is possible with current technology and draws the conclusion that we already have the computing capacity to take pictures with solar gravitational lensing, if not the spacecraft. All you'd have to do is launch a detector of some sort and line it up with the sun and whatever it is you want to see. Of course, this is not without its challenges. Let's hit some of the big ones the authors identified. First, the sun doesn't have a perfectly sharp edge. It has an atmosphere called the corona, and the corona would block a lot of what we'd like to see. So we would need sophisticated ways to correct for that. Second, we need to put our detector far enough away from the sun to actually use it as a gravitational lens. This is far away, around 550 astronomical units from the sun. That's 550 times the distance between the sun and the Earth. For context, Voyager 1, the most distant craft we've ever sent into space, is a bit more than 150 AU from the sun. And finally, these telescopes would, in effect, be single-use. You need them to be perfectly aligned with whatever they're observing. So if we want to observe the Alpha Centauri system, we need to send out a telescope specifically for the Alpha Centauri system. If we want to observe the TRAPPIST-1 system, we'd need a totally different mission. But the big win of this study was that they actually offered a simulation of what the Earth would look like if it was about 4.3 light years away, and we were able to take a picture of it this way. This is what we would get before correcting for any fuzziness from the sun's corona and the fact that it's not a perfect sphere. This is what we would get after correction. It seems impossible, but this is likely a thing that humanity really could do. Probably not super soon, though. There are a lot of challenges to overcome, and probably a number that are yet to be uncovered. And even if a solar gravitational lens was built, it would take, with current technology, at minimum 17 years to arrive at the proper focal distance to start doing astronomy. But I really want to see those pictures, so TikTok astronomers.
Yeah. Don't leave us hanging. If you don't want us to leave you hanging, you might like a few of our other videos about famous observatories, like our farewell to the Arecibo radio telescope. And thanks for spending some time with us today.